wait a moment, and then we can start.
This is Tencent.
Yeah, still Tencent. Okay.
Do you need you need to pay for an account so that you in order to record lectures?
So one may need to pay something to enlarge the storage to record the videos. Yeah, you can start. It's not recording.
All right, back to the door. All right, so let me know when I can.
Yeah, you can start.
All right, so today I'm going to talk about multiple zeta values. So let me just in fact, I will talk more about identities involving multiple zeta values. So let me remind you that these are probably defined this way. And of course, so for K1, Kr minus 1 greater than 1, and Kr greater or equal than 2, we define these numbers. So these are real numbers. In convergent series, very slowly convergent series. All right, and the goal was to understand. So it was to understand two linear relations. Among these multiple zeta values. That was the goal. And for us, towards achieving this goal, we had some kind of Stoffel relations, shuffle, double shuffle, and of course, when you combine the two, and regularization. So with the regularization, we can recover also the divergent multiple zeta value. So this is the goal. We want to understand this. And now I'm I mentioned a bit last time. I hope it's big enough.
Yeah, it's big enough.
I mentioned this last time that this integral representation of multiple zeta values of Kontsevich, so which started from this, from the example of Leibniz. Right. And we want to see if we can find a much more general representation of multiple zeta values. All right, so today I'm gonna, we would like to express more multiple zeta values in terms of this integral representation. And in fact, I would like to prove there is this theorem of Kontsevich. But before I go into that, let me just, so as you can see here, I have these two one forms. So for, we consider a set of complex numbers, and I take out these 2 points. So we consider this one forms omega 0. So this is dz over z, and omega 1 dz over 1 minus. So as you can see, this is can be expressed in terms of that. Well, there was this result, this theorem of Kontsevich, and in fact we will prove this. This goes back, I think, in 1997, if I'm not mistaken. It's a funny story here, because you will see there are a lot of things involved. But anyway, we'll get to that. So basically, Kontsevich proved the following. So he showed that multiple zeta values can be written in this way. Oh, sorry, is this? Anyway, this is the integral. So I'm going to write it generically like this from 0 to 1, but in fact it's the iterated integral. So this is omega 1 and omega 0 k1 minus 1 times and keep going. Right. So as you can see, for example, zeta of if we take, for example, our k equals r equals 1, so when zeta of 2, or for example, you recover exactly the previous one. Or for example, if you want to write, let's write zeta of 3, right? So in weight 3, we have a single zeta. So you write it as an iterated integral. You have weight 3 now, pay attention. So you have these, and it will be the same dt1, 1 minus t1, dt2, t2, and dt3 over t2. But if you want to write a double zeta value, let's say if you want to write zeta of 1, 1, 2, and we know that we'll do, thanks to Euler, zeta of 1 to zeta of 3, but as an iterated integral, so you have again weight 3 here. So you'll have dt1 over 1 minus t1, dt2 1 minus t2, dt3 over t. So you can write it in this way. And of course, we would like to, well, we saw this last time when we multiplied two single zeta values, we obtained some relations, right? All right. So now we would like to prove this result of Kontsevich, right? In fact, let me mention this one thing here. In fact, multiple zeta values, what we mean by that is that, let me write it here, multiple zeta values are periods in the sense of Kontsevich-Zagier definition. Right. In fact, there there are other constants that are periods. For example, pi is a period, right? You can write it as an integral. You can also write natural log of 2 and so on and so forth. Anyway, so for this to prove this, let me just I will introduce a function. So the idea is to introduce this function of multiple polylogarithms functions of single variables. Put here a single variable, because I can also have multiple polylogarithm functions of multiple variables. So let me just write this for several variables. And so for several variables, we can write it in this way. And you will see that this is just a generalization of, you will see you will obtain the multiple zeta values in a particular case. So I have here z1 and zr variables. Here I have k1 to k1. And here I have z1 and 1, Z star to R. So these are the multiple polylogarithms, right? And for a single variable, let's just deal with one. So I'll write it for a single variable. Let me just keep the last one. So we'll keep Li of K 1KR, ZR, and I'll have this. ZR and R. And at some point, generically, since it's just a single variable, I will just write it as Z to the power. And so this is N1 to K1 and NR to KR. Well, it's quite clear that well, obviously, if we evaluate at 1, we obtain a multiple Zeta values. At some point, instead of me writing K1, KR, I'll put a K, a big K, let's say like this, so that I don't need to save some effort. So let me just notation-wise, this would be Li K of 1 is Zeta of K. In this multiple Zeta, right? So instead of me writing all these indices. So, and of course, since we introduced this variable here, we need some kind of a functional equation in order to write some kind of relations between these. Maybe we'd like to see, in fact, we saw last time that there is a relationship between the dilogarithm, trilogarithm, and so on. When you differentiate, you'll get the one from the other. And in fact, we use this, we proved it in a very fancy way that zeta of 1, 2, zeta of 3 Euler's identity. All right. So we need some kind of a functional equation. So we need functional equations. And don't imagine that we need something very fancy. We need something very trivial, I would say. So for this multiple polylogarithm function, right? Well, and that will be very similar to in the case of polylogarithm or of dilogarithm and so on. So what we're going to do is the following. So I'm going to find out the integral representation of the polylogarithm, right, of a single variable, and then the limiting case of z goes to 1 would be recover exactly the multiple zeta value. So that's exactly what we're going to do. But first, let me just say a few things about this function, maybe a little bit more. Actually, it's very used, to my surprise, but it's very useful in physics and quantum field theory. They use this a lot, especially when they want to describe Feynman amplitudes. Let's discuss a bit about this function. And in fact, we would like to see how we're going to integrate and what kind of a relationship is, there exists between these polylogarithms. So let me just state a proposition. Well, I'm not going to prove this one. It's just like in the case with Riemann zeta functions, and we would like to see how this will extend to the whole complex plane. So Li of K, so once again, I stress out that this guy here is multiple. right, is holomorphic on the open disk and moreover this can be continuously extended to the closed disk, and of course, as you can imagine, when we evaluate this at 1, we will get exactly the multiple zeta values, just like this. Right. So that's a theorem in complex analysis. And like I said, well, we like to find some kind of functional equations. Well, there are plenty of functional equations that multiple polar logarithms satisfy, but the easiest one is given by the following. Let me just write it. So proposition 2, and in fact, this will be a key ingredient in proving Kontsevich theorem. So the following identities are true. So let me write the first one. In fact, both of them will be, just like I said, key ingredients for Kontsevich theorem. In fact, we would like to see how we're going to integrate the multiple polar logarithm function with respect to those two one forms. And in fact, we'll have this, that the interval from 0 to z, let's say, right? These are true for all z less than 1 of Li of k. Let me put generically here TR. dTR for TR. This will be Li of, and in fact, maybe I should, okay, maybe I should be specific here. Let me be specific because something will happen to the indices. KR, right? This will be equal to Li of K1 of KR plus 1, and we add 1 of Z. And the second one, the interval, we like to see we're integrating this with respect to the second one form. So KR of TR dTR over 1 minus TR. And this will give us Li of K1, okay, Li of K1 KR minus 1, KR and 1 here of Z. So these are the easiest functional equations. Let me write it here. Easiest functional equations for polylogarithm. Wait, why do I say they're the easiest? Well, basically, just in fact, let's just sketch the proof, and I think I have enough room here to do that. So let me do it here. So the thing is that here I just use the definition, right? I just use exactly. So the first one, well, you can just write it directly. Just by using, in fact, Li of K1 KR of TR dTR TR. As you can see, I will write here. So this would be, if I'm writing this, so this would be the integral from 0 to z of t r to the nr times dt1 over, sorry, dtr here, dtr over tr. Well, here we're just basic algebra, and at some point this will give us it will give us exactly this, because when you integrate, you will get exactly this. So this is actually very true. In fact, I don't even need to write it. The second one, well, it's a little bit trickier, right? So the second one, you just need to write this as a geometric series. In fact, I don't need to prove this since we're just a seminar, we're not in a class. So you just write this. So for the second one, you write, the idea is to write 1 over 1 minus tr as a geometric series. Tr to the top. And you do the same thing. And at some point, you'll have an index which is larger than all these n1 to some n something to another power, which will be 1. So that's why you get 1 here. Yes.
It seems from those two identities that the function you got, the new Li function you got, is the primitive function of the integral, right?
Yes, 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 exactly.
And can we just check by taking derivative?
Yeah, you can also do it. It's basically the same thing. All right. So now the result of Kontsevich, so I'm postponing it a bit because I would like to write this multiple polylogarithm as an iterated integral. So let me do that. In fact, that will be in fact, the proof will be just an induction over the weight. So let me just write it in this way. So theorem for z between 0 and 1, we have that the multiple polylogarithm of a single variable can be written as this. Pay attention again, it's an iterated integral, but I'm writing it generically like this, of some kind of product of one forms. I'm going to write them like this, where these one forms, in fact, you can write them explicitly, or explicitly written in terms of maybe the notation was not the best one, in terms of omega 0 and omega 1. And when I say here this k here, maybe I should put it like this, because it's right. And in fact, the limiting case as z approaches 1 will, the limiting case will recover exactly the multiple zeta value. So the Kontsevich theorem will follow immediately. All right, so Kontsevich. And the proof of this followed by an induction. On the weight. We do an induction on the weight and the proof will follow. So Kontsevich theorem follows immediately. So in other words, we have that, let me just write it again because I would like to use a notation from, so zeta of k this is the integral from 0 to 1, omega 1, omega 0. And we keep going. And I think at this point it's pretty easy to express all the others integrals. If you want to write in any way you want, you can write this as an iterated integral, right? We have seen previously. So, and of course you can play around with the, in fact, I was playing around with some examples when I multiply zeta of 2 and zeta of 3. Actually, there are 10 integrals. You should be very careful when you multiply them. So, anyway, it's like a shuffle when you shuffle them. All right. So now I'm going to use the following notation. Because I don't want to write this integral all the time. So I'm going to write this in the following way. Because at this point I'm veering towards something. I'm not going to tell you what it is, but it's something very nice. So I'm going to write this as integral, right? I'm going to denote this by I. So like I said, that's why I write it generically. So if I start from 0 and I end up at 1 here, I'm going to put 1. And then I'm going to put, since I'm dealing with these two 1 forms, I'll put 1 from omega 1, 0, k1 minus 1. 1, 0, kr minus 1, and 1. So that's the iterated integral of Kontsevich. So 0 and 1 appear at the endpoints of the integral. And of course, well, I can express this if you want to, maybe I'll talk a bit more about this next time when I'll discuss the Hoffman algebra of multiple zeta values. This actually are chain iterated integrals. So there are something like this. Omega 1 T1 omega k tk, something like this. And now what I'm going to do is the following. So let's look at this, because I want to, so as you can see, the endpoints are 0 and 1. So when I'm going from 0 to 1 with t, I'm going back to, I can do this shift with 1 minus t, right? So what I'm going to do, I'm going to make a change of variables. So, and you will see that we will obtain what we will call the duality theorem. In fact, I'll write a couple of, I'll write it in terms of this new notation, and then I'll write it explicitly in terms of multiple zeta values. In fact, we will call this duality Drinfeld theorem. Now we'll explain how it got this name. In fact, this is related to the work of Drinfeld back in the days with Hoff algebras and everything, when he got the Field's metaphor. I'll just explain a bit. Well, I don't know details about it, but I've read the book. So now let's change the variable. So when we change the variable, we take t to go to 1 minus t. And let's look at this integral, right? So when we change the variable, that integral will become what? So we'll have that, well, the endpoints will change, right? We'll have 1, 0, 0, 1, k minus 1. So I'm going to change 0 with 1. Now I have here a minus, right? 0. But now, if we, well, now we can interchange the, we can reverse the path of integration, and this would be nothing else than just I of 0 0, 1, k1 plus 1, kr minus 1, 1. So as you can see, we started with this integral, we ended up with this. In fact, wait, what did I do? No, I think I made a mistake here. Should be wait. Yes, okay. So let me so this is what we will call Drinfeld duality. In fact, I'll write it explicitly. Let me just give you a quick example. And the quick example I have in mind is, again, let me go back to Euler's identity. Right, zeta of 1, 2 equals zeta of 3. All right, let's see here. So zeta of 1, 2 can be written as I of 0. So I have here what? 1, 1, 2, 1, 1, 0, sorry. Right? 1. And now what we're going to do is we're going to reverse and interchange 0 with 1. So when we reverse and interchange, this would be I of 0, so reverse and interchange. So 0 more 100, right? 1 0 0 1, which is exactly zeta. So reverse and interchange. In fact, I use this abstract notation because when I'll discuss the Hoffman algebra, we need some kind of notation like this. But now let me write it explicitly. So in fact, I will write the Drinfeld duality explicitly. So that in terms of multiple zeta values. So basically, that identity with integrals that I just wrote can be rewritten in the following way. And in fact, I will give you two versions: the weak version, what I call the weak version, and the strong version of Drinfeld duality. So this is a theorem, which I can say Drinfeld. People attribute this to Drinfeld. And in fact, okay, let me write it and then I'll tell you the story. So the weak version is the following. So zeta of, and I'm going to write it in this way, I have here, let's say, m copies of 1, and then n plus 2. Then this is the same as 1 n copies and n plus 2. And these are for m and n non-negative integers. Right? This is exactly what we interchanged. This is exactly what we did with the integral. So this is the weak version. And in fact, I'm going to write this in the following way. Zeta of 1, n copies of 1, n plus 2. Just for the sake of saving some space. So this is the weak version. And now the strong version, which again follows from is the following. So you see, I have only m copies of 2, then I have a value, n plus 2. But maybe you're wondering, well, maybe these copies of 1, maybe they can repeat each other. Can we do that? In fact, we can. And that's what we call the strong version. And let me just, so let me denote this. Let me say that M is MR. And N is this set of numbers, and R. And M bar will be, all right, so this will be in increasing order. I'll write them in reverse order. So MR, M1, and N bar is NR, N1. All right, so now what we're going to do, we're going to define this family of multiple zeta values. In fact, we're going to call this the Drinfeld. I'm going to denote this by dmn. So this will be the zeta of, so I'm going to have, again, one copy, nr minus 1 copies of 1. Then I will have here mr plus 1. Well, as you can see, the weak version stops here, but now we'll continue. Then I have, and I keep going. Then I have n1 minus 1 copies of 1, and then m1 plus 1, right? So I'm going to denote this by this. Then Drinfeld duality. So then dmn is nothing else than just dn bar m bar. In fact, let's write it explicitly so that we can see it better, because I like to play with it a bit. I'd like to see some examples. In fact, we will see how we will obtain some of the examples from from last time and the first time either. And in fact, the example I want to dwell more on it will be I would like to go back to multiple zeta values in weight 5. So so let's write it explicitly. So explicitly, this is zeta of, I can write it in terms of integrals if I want, but let me just write it with zeta. This is, so nr minus 1 and r plus 1. I have n1 minus 1 copies of 1, m1 plus 1. And now, so this will be a zeta of, and now let's be, so it's n bar, m bar. So this will be, so it will start with m1 minus 1, right? And 1 plus 1. And we keep going. I'll have here mr minus 1 and r plus 1. So this is Drinfeld duality, and it's more more general form. So that's what we call the strong version. And now let's see some examples, some consequences or applications, whatever that call them, consequences, because they're pretty easy. For example, let's see the weak version and the strong version. So let's see. Okay, let's start with Euler again. So this again is identity from 776. Zeta of 1, 2 equals zeta of 3. I think this follows immediately from the weak version, right? So it's the weak version for for what? For m equals 0 and n equals 1. But actually, we can prove even more, maybe generalized Euler. We can actually prove that if we have, let's say, k minus 2 copies of 1 and a 2 here, right? This will be zeta of k. So in particular, you recover Euler. So this is again the weak version. So you take m to be k minus 2. So weak version for m to be k minus 2 and m to be 0, right? Well, actually, can we go even more? Well, there's probably you're wondering, what if we have something like this? This is a Hoffman identity. This was Hoffman, let me say, 1992. It was in his paper. I think I told you. Michael Hoffman and Don Zagier wrote independent papers. One of them, Michael Hoffman called it multiple harmonic sums. Don Zagier called them multiple zeta values, but in fact, they were talking about the same thing. And in fact, he proved the among other things that we'll talk about today. More or less, I will discuss the identities proved by Michael Hoffman back in '92 today. And this is one of the first. So what if we have something like this? So zeta, I have 1, 2, and I have n copies of 1, 2. So this will be, guess what? So zeta of 1, 2, 1, 2, 1, 2 is zeta of 3, 3, 3, 3, 3. Well, the thing is, it doesn't quite follow from the weak version, so we need to use the strong version. So just take, so this follows from the strong version for, well, we're going to take all the mi's to be 1, and all the ni's to be 2. And then you'll get exactly 1, 2, see, and get here 2. Wait. I think this is the other way around. Anyway, something like that. You'll get 1, 2, 1, 2, 1, 2. You'll be here 3, 3, 3, because here I'll take. I want them to disappear from here. Maybe I should take m. Anyway, something like that. So this will follow from the strong version. And also, well, let me go back to multiple zeta values in weight 5. Because I've said a bunch of them. And I think there were a bunch of them. So there was zeta of 5, zeta of 1, 2, 3. No, okay. 1 of 4, zeta of 1, 1, 3, zeta of 2, 3, zeta of 3, 2. What else? Zeta of 1, 1. Actually, 1, 2, 2. Zeta of 2, 1, 2. 1, 2, 3, 4, 5, 6, 7, and I'm missing 1.
1, 1, 1, 2.
Yes, 1, 1, 1, 2. Exactly. So these are the 8, and we said that 6 of them are linearly independent. In fact, most of them will depend on these ones. And I said that we have a bunch of relations. In fact, we can get rid rid of some of them. For example, we can express for example, look at these ones from the Drinfeld duality. So from the duality, we can write zeta of 113 as zeta of 14. We can write zeta of 1, 2 is zeta. Well, actually, let me just write them in weight of 5, and that's it. What else do we have? Zeta of 1, 2, 2 plus, you can write this in terms of zeta of 2, 3, and you need the strong version for this. And then you have zeta of 2, 1, 2, and this will be zeta of 3. So in weight 5, you have, and of course, what else do we have? Yes. And of course, okay, zeta of 5, zeta of 1, 1, 1, 2 is zeta of 5. So by the duality, you can write these relations. All right, so actually, I'd like to make a comment. Well, I wanted to actually prove this, but since I have, oh my God, plenty of other things to say, there's a also if you want to see a different proof that for this one, for Hoffman identity, there is a one by Zudilin, I think in 2017, it's a paper. I think it's on archive. But in fact, I will show you a prototype how to prove these kind of multiple zeta values identities. All right, so now putting everything together, you see that we have like from shuffle, shuffle, double shuffle, regularization, and then from the duality, we can write down some relations among these multiple zeta values. But there is not enough. That's not enough to find all of them. And let me give you another family. And I think I said this last time, and I'll prove it now. Maybe I'll show 2 proofs of this. For the simplest family, Hoffman family of multiple zeta values. So this is another theorem from the paper of Hoffman. In fact, I'll call this identity Hoffman-Zagier because Zagier proved it as well. I don't know what to say. I put the year 1992, although it's quite unclear because Hoffman published the paper 92. Zagier, he had this memoir at the European Congress in 93 or whatever. Anyway, so let's call it Hoffman-Zagier. So this is the, let's call it HR, and this will be zeta of 2. I'll have 8 R copies of 2. So let me write it in this way. This is 5 to the 2R over 2R plus 1 factorial. So as you can see, well, if you look at it, right? For example, for R, let's say for R equals 1, this is zeta of 2, which is pi squared over 3 factorial, which is 6, which for R equals 2, we have zeta of 2, 2, which is pi to the 4th over 5 factorial, right? So, which is exactly 5 to the 4th over 120. Exactly the value that we found when we used the Stocker product, right? But in fact, maybe we could, what if I have something like, let me just, for r equals 3, maybe there is a way to find for r equals 3, so zeta of triple zeta of 2, 2, 2, this will be pi to the 6 over 7 factorial, whatever that is, right? And in fact, let's see if we can find this. And I'm going to do the same trick as I did with the Stoffel product. So let's use the Stoffel product. Because maybe I'm, in fact, when there was a talk, it's actually, it's on YouTube, with Zagier, multiple zeta values, it's called. Like a 2 hours, 3 hours talk. It talks about everything. Very fast. You have to, anyway. And he says about this equality that can be easily proven by induction. I'm not sure what he meant by that, but I'll sketch a proof. Maybe it's trivial for him. But anyway, let's go back to this example. So if I multiply, let's say, a single zeta value, right? Zeta of 2 and zeta of 2, 2, and maybe I'll try to use the Stoffel product. So let's see, what do we have? So we have zeta of 2, 2, 2 plus zeta of, so I'll put here, I'll put here, I'll put here. So zeta of 2, 2, 2 plus another one, zeta of, so 3 zeta of 2, 2, 2 plus, and I have zeta of 2, 4 plus zeta of 4, 2. And of course, I can find these two. If I do the Stoffel again, the Stoffel product with these two, this will be zeta of 2, 4 plus zeta of 4, 2 plus zeta of 6. And of course, I can write down everything. I can put these ones here. I can replace and I can find the value for zeta of 3, 2, right? So zeta of 3, 2, 2, 2, 2, it's some explicit value, right? So you see, in this way, I'm building this relations. And of course, if you want to write down for the fourth one, then you hope. Anyway, so you can check by just computation. You can check the computations here just to see if they match this value. Anyway, I don't want to do it here. I don't want to embarrass myself with making mistakes in trivial algebra, especially when they're on camera. All right, now let's prove this. And in fact, I have two proofs, and I hope try to. Maybe I'll just, don't need to write in great detail everything. In fact, let me give you the generating function one first, and then I will just prove it by induction. So let's see, proof one. In other words, what is the idea? The idea is to look at the certain generating function. Anyway, don't tell me how I came up with that, not yet. You will see that it's a standard way to come with this generating function. So I would look for a generating function whose coefficient will be zeta of 2, 2, 2, 2. And then I will try to expand it as a product. And if this generating function, this infinite sum is that infinite product, and if by some miracle that infinite product is some function, some, I don't know, easy hypergeometric function, which in this case will be sine, then I can write the power series expansion. So I'll have a sum, then I'll have, so I'm going through a product, and that product will become again a sum, and then I'll just identify the coefficients. So that's the trick. And you can always apply this trick when we try to find non-trivial identities for multiple zeta values. Now let's get to the details. So the details is so we have the following proposition. So I'm just gonna write the generating function for multiple zeta values with when all the indices are equal. So the generating function of zeta of k, 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 right, times x to the n, this guy here, so I'm writing in general, this will be equal to the product overall j greater than 1, it's infinite product, 1 plus x over j to the power k. You can see, and this, well, actually, this is trivial to see, but this furthermore can be expressed as the exponential. So this is e to the this infinite sum, this series x to the s over s, and here I have the zeta of ks. So this is the identity. Well, in fact, the first part is very easy to see. When you expand this, right, as a product, you'll have, so you'll have what? You'll have 1 plus then the sum 1 over j to the power k, j greater than 1, plus then the next coefficient will be the sum over all j1 less than j2 over j1 to j1 to the k and j2 to the k, and so on. In other words, you have 1 plus zeta of k times x plus zeta double zeta of k times x squared, and you keep going. And now for the second equality, this is not as trivial as the first one. Actually, we have to kind of use the logarithmic derivative. Anyway, it's just like a calculus 1 trick, nothing special. So for the second equality, you will have something like this anyway. I'm just going to write it. I'm going to skip the computations. You'll have something like, so when we want to prove this for the second equality, we have something like, well, in fact, let me consider this function, you know. Let me denote this by fk, f sub k of x, so that I can see it better. So if I'm denoting this function, and I could take the logarithmic derivative by fk 5 of x or fk of x, and after some computations, I'm going to skip that. In fact, I hope I did them the right way. So this will be exactly something like this. The sum over all L of negative 1 to the power L minus 1 times x to the L minus 1 times zeta k, something like that. Anyway, and then you just integrate, and then you will get the set. All right. Now the thing is that how to apply this this prop.
That's the same as L. You're saying either L and S.
No, actually, it should be here L, I think. Okay, X. Sorry. Yeah. Yeah. And now the thing is that we want to recognize this. You see, I'm looking at this product here. So maybe I should recognize this. So let me just go back to this function. Maybe we can recognize something. Let me take k to be 2. So take k to be 2 because we're interested in evaluating this. And my function fk, f2 of, and now let me change the variable. Let me put negative z squared because I would recognize this. This will be what? If you recognize the sine product function, this will be nothing else than just sine of pi z over pi z. So the infinite product formula for sine it says that sine of z is z times the product right? So we use this. So in this way, this product will be exactly this. And now, guess what? Well, on the other hand, we can expand this by its Taylor series. So on the other hand, we have that f2 of negative 2z squared, which is, like I said, sine of pi z over pi z. And this will be if we, well, I put here n, but anyway, so this will be the sum over O n, 0, negative 1 to the n times, let me write it here. So here I use the Taylor series for the sine, power series. And this will be, so it's negative 1 to the kz to the k, 2k plus 1 over 2k plus 1 factorial. So this would be, let's see, what do we have here? So negative 1 to the power k times p to the power 2k plus 1 over, sorry, pi to the 2k plus 1. So pi to the 2k over 2k plus 1 factorial, right? Times z to the 2k. 2n, sorry, put n here, so that I can right? So f2 of negative 2z, if we replace there, I'll have again a negative 1 to the n, right? Here, so we'll get exactly, as you can see, I have the two functions. The coefficients should be equal. So in that case, would be this would be the sum to, and here I have a negative 1 to the n. Sorry. Z to the 2n. So we identify the coefficients, and there you go. So zeta of 2 is pi to the 2n plus 1 over pi to the 2n over 2n.
Why is f2 minus z squared equal to sine pi z over pi z?
Where?
F2 of minus.
Why is this?
Yeah. Why is
by
this?
the sign product formula, you see when you replace here by negative, you'll get exactly the sign product formula here.
You replace x by minus.
You
z
replace,
squared?
you see, yes, yeah, x by negative z squared, yes.
G squared is, okay. see.
So you'll get exactly this. So this is the ingredient missing here. So in other words, yes.
Why do we need the last expression?
This one we don't actually. Just to wait. Actually, I should have mentioned this anyway. I forgot. This expression is another fancy way of proving Drinfeld duality maybe I'll do it.
It seems that, like, for example, if we expand the last expression in power series, maybe it's a double power series, right? Then we can get a linear combination to represent the zeta k. Is that true?
Yes, exactly. Exactly. It's like the polynomials in Zeta. Yes, exactly. Yeah, exactly. Yeah, that's actually a very good observation. So, in fact, there is another way of proving this. I'm not sure if I have time, but let me just mention it. In fact, I was like searching for. I saw that Zagier video. He was saying that we can prove this by induction. Actually, I tried to think of how you can prove this by very easy induction, and the proof that I came up with is not. I mean, it is. I want to say it's the most trivial, the easiest proof. But let me just mention it quickly. There was another thing that I wanted to discuss. And in fact, I'll tell you a general story how to come up with these generating functions. And of course, by Dongshen's remark, you can actually prove for zeta of 4, n copies of 4, 6, and so on. So you can do that. But there's a second proof. I'll just by induction. I'll just mention it briefly. So I will just. So basically, I will write this as a symmetric sum, right? So write h of n, write zeta of 2 as symmetric sums. So the way I'm going to write this in the form. So if we define the elementary symmetric sum, x1, x2, and so on. xn1, xn2, xnr, right? If we do, so hn will be nothing else than just er of 1 over 1 squared, 1 over 2 squared, and so on. All right. So I'm trying to prove by some kind of induction. So if I'm doing this, I need some kind of a recursion for the values of the zeta, of the Riemann zeta. I need some Riemann zeta values. So for r equals, okay, h r here, whatever. So for r equals 1, we have e of e1, which is nothing else than zeta of 2, which is pi squared over 6. And now, if we, I need to come up, I need to do something about the induction hypothesis. So for the induction hypothesis, we have this Newton sums. Which can be expressed in this way. Bj of x1, x2, and so on, and this will be E r minus j x1, x2. And of course, Bj, let me just say who this is, or PR in general, is x1, x2, and so on. this is the sum of the series of all. All right. So, so I assume by induction that all values were for an R prime between 1 and R. Less than R is R is exactly 5 to the 2 R prime 2 R prime plus 1 factorial. And I'm trying to prove this. So using this, right, I will have something like so this guy here will be zeta of 2j. And the only thing I need here is just by to use, when I'm going to be sketching the details, is this what we call a song recursion formula on the inductive step. Which is a pretty amazing identity, actually, which says the following. So -1 1 to the power R times pi to the 2R over 2R plus 1 factorial plus the sum from j equals 0 to r minus 1 pi -1 to the power j pi to the j to the 2j over 2j plus 1 factorial. Zeta of 2 r minus 2j. So this is equal to 0. So we have this some recursion formula, which, and by some miracle, putting everything together, everything works just fine. And as you can see in this recursion, we have this. Anyway, I don't want to deal too much on this thing. I just thought about it. And now in the remaining time, well, there was one identity that I wanted to mention. And I think after this, I'm going to stop. Which was a conjecture of Zagier in the early days of multiple zeta values. In fact, if you read Zagier's one-page manifest from the European Congress of Mathematicians back in '93, in fact, he talks about the evaluating zeta of 2, 2, 2, 2, then the Drinfeld duality. But then at the end, he says something like, well, there was a conjecture of Zagier. In fact, we have seen how to evaluate zeta of 1, 2, 1, 2, zeta of 2, 2 to 2, and so on. But the question is how to evaluate this family. 1, 3, 1, 3, 1, 3. In fact, it has a value, and it can be expressed. So this is 2 to the pi to the 2 times pi to the power 4n over 4n plus 2 factorial. So this was a conjecture of Zagier. And in fact, this confirms the fact that if we remember when we looked for n equals 1, we have zeta of 1, 3, which is 2 times pi to the 4th over 6 factorial, right? And in fact, we proved from the shuffle relations that zeta of 1, 3 is 1 over 4 zeta of 4. In any case, again, this is like pi to 4 times the right hand. So now the question is, if we can generalize this, just like we said, like zeta of 1, 3 was zeta of 3, and we generalize this, Hoffman generalizes to zeta of 1, 2, 1, 2, 1, 2. So this would be zeta of 3, 3, 3, right? Maybe we can generalize in this way. So Zagier asked this question in 93. And it was solved, the conjecture was solved by David Broadhurst, physicist. I think in 97 or 98, I don't recall exactly the year, but I think it was funny because the paper was, there were 4 people in that paper. And in fact, maybe I would rediscuss this identity maybe next time when I'll talk about more about the algebra, the Hoffman algebra of multiple zeta values. In fact, this comes like a consequence of operations in that Hoffman algebra. But today, well, the remaining time, let me just give you a very clever argument of Broadhurst, like a very. So the way he solved it was like a very using a clever hypergeometric argument. In fact, you will see that all these functions are hypergeometric functions. Geometric argument. Right, even sine, it's again a hypergeometric function. And let me just state, maybe I'll just mention a bit his argument. So when I say hypergeometric argument, I mean using Gauss hypergeometric function. In fact, this function is just a generalization of all the elementary functions that you know, exponential, sine, cosine, arcsine, logarithm, you name it. So the way it's defined, let me just mention briefly the property. In fact, the state of property that we will need in the proof of this. So so the Gauss hypergeometric function, the way it's defined is 2f1, a, b, c, and let me use the variable z. So it's defined in this way with this function. And these are the Polyhammer symbols. Z to the end, right? And this is the Polyhammer symbol, right? It's just a and a plus 1 plus a plus n minus 1, or this is just gamma or gamma.
I think there's an additional 1 over.
Oh, I forgot here. Oh, forgot. So this is the Gauss hypergeometric function. And like I said, you can recover this, and this is a solution to an ODE, which is something like this: z times 1 minus z. So a second order ODE. So this is the ODE. So this is the hypergeometric function is the solution of this ODE. And of course, it has many important properties. And in fact, one of them, in fact, you can it has an integral representation. You can write down the Laplace transform, so on and so forth. I will not mention here. But there is one thing that I would like to mention, and this is a very important thing. So it's Gauss summation formula. because Broadhurst used this, which basically says the following. So if we evaluate the hypergeometric function at for z equals 1, so this will give us, we can write this only in terms of the gamma function. So this would be gamma of c times gamma of c minus a minus b. Everything will work gamma c minus a times gamma of c minus b. So this was enough to, this lemma was enough for Broadhurst to prove this. And in fact, what we're going to do is just to, when we want to prove something like this, so again, just like in the case of 2, 2, 2, 2, 2, so what we're going to do is we're going to look at this multiple zeta of 1, 3, 1, 3 as a coefficient from a generating function. And then the quantity over there, we're going to do the same thing with the coefficient from another generating function. So these two functions, actually, they're the same. So we identify the coefficients are being equal. And the way we're going to introduce this is a general way of introducing this generating function. So usually we introduce the generating function, and I'm going to do it in the following way. So this will be L of K. So when I say K here, I mean K1, K2, Kr, right? So that's what I mean. Of these variables Z, T. So this would be, and I'm going to introduce it in terms of the multiple polylogarithm. So this would be the multiple polylogarithm, right, of K1, Kr of Z times T to the power N times, I put here the absolute value of K, but this is the weight. So this is K1 plus K2 plus K. Right, is the weight of all right. So in our case, we need to see what happens if we introduce this 1, 3, 1, 3, 1, 3, right? So in our case, and in fact, we have this lemma. The thing is that how can we write this generating function in our case? So L of 1, 3 of Z of T. Well, in our case, this will be a product of very specific hypergeometric function. So let me write it down. This was the trick of Broadhurst. So one and Z, and times the product of the same thing, but here with negative I. So the same thing. We have one with negative I here. Whatever. And then once you prove this, so this is actually to require some kind of details, which I'm gonna miss, but these are actually this is basically the most important part of the proof, by expressing this generating function as a product of two hypergeometric functions. But now, after I do this, I can write this using Gauss summation formula. And once I do this and do all the computations expressing, you can express this as, for example, a particular case here. Let me just mention 2f1 of a, negative a, 1 and 1. All right, this can be expressed as 1 over gamma of 1 minus a times gamma of 1 plus a, and using what we call Euler's reflection formula. This would be nothing else than sine of pi a over pi. So the day I have some exactly that coefficient. Anyway, details.
questions? Next time, like maybe John will give a talk.
Okay.
He can do that. Then you have already gave 3 lectures. It's
Well,
a very big contribution to this seminar already. And maybe later on, we can
if I can talk about how more organized stuff.
yeah. We can switch. And anybody who will need to give a talk, and write to me or we can arrange this. So for the question, let's see that again.